and welcome back to the course Cobot Theory and Practice. In this lecture, I will discuss various collaborative modes as defined by ISO. I will discuss quasi-static and transient contacts. I will discuss biomechanical limits for the onset of pain as per ISO 15066 standard, various ISO standards that apply to a cobot, major cobot makers that are primarily reported in multiple research and production units across the world. Okay, so let us begin. So what are collaborative modes? As per ISO 102182 and ISO TS 15066, they are broadly classified in 4 categories. First one is monitored safe start kind of. The first one is monitored safe stop. So what is that? It is in this case the robot operates autonomously and it pauses safely for entering any personnel. So it could be a standard industrial robot which is there in the industry, which are position controlled. They are normally caged and it may have provision to detect human entering into the workspace of the robot. It may use safety curtain, light curtain, or a gate switch. If at all there is a fence and there is a gate, as soon as the gate is opened, it assumes the person is attempting to enter the workspace and robot stops safely without actually hampering the programming. Okay, if at all some cycle is going on, it will continue once the person goes out of the robot workspace. Okay, so that is monitored safe stop. The second one is speed and separation control. In this, the robot adjusts its speed depending on the distance from the worker. No contact with the robot is allowed. While the robot is moving, there should be absolutely no contact. What it does basically, it uses a kind of vision sensor or a lidar or a ultrasound sensor to detect the speed of the person who is coming towards the robot. So as it goes closer and closer, robot may gradually stop, right? So at certain distance it will run at a very slower speed. When it comes quite closer, in that case robot may totally stop, the way it did it in monitored safe stop condition, right? So this is the second way. Again, in this case the robot is normally standard industrial robot, but there may not be any fence or just a temporary fencing is there, right? So that is the second case. And the third one is manual guidance robot. In this case the robot is operated by human. The operator guides the robot manually using it as a high performance robot, right? In this case the person is able to take the robot to certain place manually by pressing a kind of button which releases the brakes and it allows human to drag the robot to a place. That is normally useful in programming, reprogramming, or maybe doing tool teaching and those kind of maintenance stuff. Okay, so this is again a standard industrial robot. Not much safety guidelines are followed here apart from standard industrial safety guidelines and robot safety guidelines. That's all. Cobot is not there in the picture still. So this is a standard industrial robot which allows doing so. And the fourth one, that is the final one, is power and force limiting. So in this case, safe human robot contact is established. In this case, human and robot, they are in contact with each other. Force is verified before it is being applied and it is limited by power at the joints, power that goes at the end effector, so that humans whosoever comes in contact with such robots, they are safe as per cobot standards. Okay, so these are standard cobots. It may have impedance, stiffness controller at the joints or at the end effector level. Okay, so this one is actually a cobot. So that's what. So even PFL, any standard cobot, may also allow manual guidance, and this also can take any of these into account as well, because just having a cobot, there is an assumption that your workspace is 100% safe. It is never the case. you may still have to follow monitored safe stop in certain cases. It depends on application to application basically. So, these guidelines are still followed, right. Apart from this being a PFL robot like a cobot, so that is the case. So, that are total 4 types of collaborative modes are these. So, what is PFL? Basically, this in short is known as PF and L, pressure force limiting. We'll also learn about quasi-static and transient. I'll also discuss quasi-static and transient contact here. The robot shall be designed to adequately reduce risk to an operator by not exceeding the applicable threshold limit for quasi-static and transient contacts as defined in Annexure A ISO TS 15066. Okay. So, mind it, all the standards that I am showing here, over here it is 2016, that is the year in which it was published. So, it is revised in timely manner every 5 years normally. Okay. So, it may change over the time, and all these definitions and few modifications could be there without your notice, right. So, yes, that is to be noted down here. So, what is quasi-static and transient contacts? What exactly is contact first of all? So, contact could be due to an intentional operation. It may be trying to measure something, right. You take your robot to some place and you want to measure the coordinate or forces or something, right. So, or maybe due to teaching. So, that could be intentional, it could be incidental. You have programmed to do it something and then it overshooted or it did something, or primarily because of program failure or something like that. And the third one is due to the total failure of the robot. Let us say one of the joint totally failed, it break, collapsed, or in those cases the robot may freely fall or some kind of such things. So, those contacts are also there. But yes, in all these contacts, as far as the cobot is operational, then only it is defined. It may be failure in programming, it may be failure of one of the joint. In all the possible cases, it has to follow quasi-static and transient contact forces which are defined next. So, what exactly is quasi-static contact? This type of contact is normally for longer duration. Limiting criteria is peak pressure and forces that actually produces stress in with is basically produces the stress on the person on which it is in contact with, right. The body part gets clamped between the part of the moving robot and another fixed or moving part of the robot cell. Over here it is shown hand is getting trapped, right. It is clamped between the table and the robot two fingered gripper. Okay. The person cannot move out his hand. Okay. So, this is one of the case. It could be possible that robot has clamped you against the fence, right. So, that could be another case. So, this is basically quasi-static contact. Okay. The next one is transient contact. In this, the contact duration is less than 0.5 second. The limiting criteria is again peak pressure and the forces that are to be controlled. Energy transfer, this is an additional thing that has to be taken care of also. This basically is the power density that goes into the robot when it does such task, right. So, not necessarily a task, it may be due to incidental or it may be due to the failure also. The body may recoil or retract from the moving part of the robot. Over here you see there is pretty good amount of space at the back of the person. He may come out of the robot workspace totally. So, that way, so this is known as a transient contacts. Okay. So, now total biomechanical limits are there for the onset of pain. This pain is also defined in ISO 15066-2016E, right. So, it has split the body into 29 body areas. The maximum allowable pressure in case of quasi-static contact is 110 to 300 Newton per centimeter square. This is as per quasi-static contact, and maximum allowable force is 65 to 220 Newton depending on which part of the body it is, right. And same in case of transient contact, it is maximum allowable pressure multiplier is that, and over here it is 2 times, except for the transient contact should not happen in the head areas, okay, the areas which are related to the head like face or forehead or skull, like that, okay. And same maximum allowable force multiplier is 2 times for except for the head areas. So, this limits, all these biomechanical limits were estimated by 3 repeated tests on 100 healthy adult subjects. This was a project which was done at University of Mainz, Germany in 2014, and you can find it out FP0317, that report is there, I have referred it here, okay. So, yes, this is the normal operating region of the cobot, okay. Normally it is favorable, you should work in this region. If at all it establishes the contact, it gets into the region of pain. So, as soon as the contact is established, so this whole region is for the pain, okay. The pain has already started and there comes a threshold over here. In this case, if it goes beyond that threshold, injury can happen. It may be a minor injury, it can be reversible, it can be irreversible injury as well, okay. So, the threshold remains still, here only, okay. So, onset of pain is defined as per ISO 15066. This is adapted by the study which was conducted here, okay. So, this is it, okay. So, this is the body model which has actually split whole of the body into 29 body areas. So, this you can refer it here, this is the link I have provided, okay. So, this is the frontal portion of your head, that is the forehead, that is the temple area, skull area is here, and you have face, you have neck, okay. So, you see there are skull and forehead, there are 2 locations, face there is 1, neck there is 2, back and shoulder 2, chest another 2, abdomen, pelvis, upper arm and the lower upper arm and elbow joints there are 2, lower arms and the wrist joint there are 3, hands and fingers there are 9. Actually it is dominant as well as non-dominant contact points are there. So, that is why it is 9 over here. Thighs and knees there are 2 and lower legs there are 2. So, altogether there are 29 contact points which are studied, okay. So, this is all about the quasi-static contact. Mind it, there is no separate study that was conducted for transient contact. So, the values which are shown here in this table are basically the for the values that are shown here, there is no, for the values that are shown here basically there is no research and are based on conservative calculations. Pressure and force limits for transient contacts are established by curves for the onset of pain for various body parts, right. So, these are basically out of conservative values and they are made out of some kind of estimation, and there is no detailed research which was done for these regions, right. So, this is very conservative values, mind it. So, only for this there are studies which were reported, right. Okay. So, what are the safety standards which a cobot manufacturer has to follow? Not just a cobot standard basically. So, these are a few. So, 2006-42 EC directive. So, that is machine directive basically, and 12100, that is the ISO standard. It is for the safety of machinery, general principles for design, risk assessment and risk reduction. It is not just for robots, it is for any general machinery, and same applies here also. ISO 13849 that is for safety of machinery. So, this is not the only thing, there are many other standards which are followed. So, that is it. And then ISO 10218-1 and 2. So, it is for robots basically, and not just for machines, it is for robots. So, a robot also has to follow machine directive. So, robot and robotic devices, safety requirements for industrial robots, part 1, that says for the robot, and part 2 is for robot systems and integration. It is for all the accessories that goes around the robot. It may be gripper, it may be turntable, it may be linear rail, and even for the safeties which are around. So, it has to take care of all those. So, it is basically very important for the integrators, whereas this one is for the manufacturer, right. And then comes the final two standards, that is ISO TS 15066, that is for robot and robotic devices. This exactly is for collaborative robots, okay, and maybe industrial robots need not to follow this one, but definitely a cobot has to follow all the above standards, okay. And ISO 13855, this is for safety of machinery, positioning of safeguards with respect to the approach speed of parts of the human body. This basically talks about the approach speed, right. So, that is there. All these are apart from ISO 9283, that is for the performance criteria of the robot, that is to obtain maybe repeatability of the robot is basically tested based on this, positioning accuracy and those stuffs are defined here. So, robot has to go through all these plus this, right, and cobot has to go through all of these, right. So, these are not just the one, there are many other standards, machine standards, which are followed by the robots, right, basically by the integrators and the manufacturers, right. Okay. So, what are major makers for these cobots? Who are the makers basically? There are many established manufacturers which were already there, who were manufacturing industrial robots. They came in. First of all is KUKA LBR. Actually, KUKA LBR started cobot making with DLR first, that came up with KUKA IVA standard. That was an adapted version of DLR arm, 7-DOF arm. First KUKA LBR 5 kg version was there, and later on it came up to 14 kg version with reach around 820 mm. That is what you can see. So, it has a payload capacity of 14 kg. Mind it, these are some of the robots, there are many other manufacturers as well. Okay, I have just listed down a few which are primarily reported by the researchers and industrial users. So, this is a few best one of them. So, it is 14 kg payload, which is pretty good for most of the industrial cobotic related tasks, not for huge payload carrying and all. So, this much is the reach, and that should be quite good enough. It is more than an arm reach of an human. Repeatability is 0.1. Degrees of freedom is as good as a human with a redundant 1 degrees of freedom, that is 7. Okay. So, that is there, and we will talk about degrees of freedom and repeatability, those aspects later in our course also. So, yes, repeatability, when we talk about repeatability, it is as per ISO 9283 only, okay. But yes, you see, you find quite good repeatability is there in case of industrial robots, but when it comes to cobot, because they are flex, they are compliant, you cannot expect much repeatability in case of cobot. So, that is the reason quite a lot of robot manufacturers, they do not mention it only. Okay, they are good robots, but yes, they do not mention it because that is for a different purpose altogether, like for say Kinova Gen 3 or Kinova Jacko, which was also a version of from them. So, they did not mention this because it may have a very poor repeatability, but yes, it is not meant to do maybe precise industrial tasks, right. It may be for a wheelchair mounted robot when human tends to do some kind of domestic stuff. Okay, in that case, that is always a human in a loop kind of operation, and that is not very significant. Fanuc, it is one of the largest capacity cobot that it is making with a very good reach also, and repeatability is reasonably very good. It is at par with a standard industrial robot. It is 6 DOF. ABB Yumi, it's a single arm that I have mentioned here, but there is also a dual arm version. Franca Amica Panda is there, that is 3 kg payload. Okay, repeatability is this 7 DOF, right? And then quite popular one maybe Rethink Robotics Sawyers. There is Baxter also, which is there. It is 4 kg payload. Baxter is dual arm, Sawyer is single arm. This doesn't mention its repeatability again. It's a 7 DOF robot. Universal Robot. Universal Robot, it is very popular. It is UR30 I have listed here. It is a 35 kg payload capacity. There are many other academic version UR5E and all, that is quite a lot of places in research paper I have seen it, and yes, this also has a repeatability of 0 point, which is quite good. It's a 6 DOF. DLR SARA is in one of the most advanced tasks is reported by this DLR SARA. For touch sensitive robot, it is reported in 24 only. Okay, so it has a very good payload capacity as well with a good reach. Yes, it doesn't mention it its repeatability, but it is a 7 DOF robot. So these are few popular industrial cobot makers. Okay, there are many others. So yes, in today's class you have learnt about biomechanical limits, you have learnt about various standards, collaborative modes, right? So that's all for this lecture. In the next lecture we will be discussing on the process of risk assessment, why it is important, how it is done as per ISO 10218 1 and 2. Okay, that's all for today. That's all for this lecture. Thanks a lot.